Our Exploravision is on nuclear fission and nuclear reactors. Nuclear reactors are a very controversial way of generating power. However, using nuclear reactors is inarguably the fastest and most efficient way of producing large quantities of electricity. There are currently many different working kinds of reactors that all claim to have the best design, and yet have many problems to still overcome. Advancements in other energy technologies are currently being made, and many of those advancements can be incorporated into nuclear power plants. We propose further developing the nuclear reactors that are currently in use in submarines and on land, and putting those proven designs in power plants on floating platforms, away from populated areas. Historically, the largest cities have been built near bodies of water, which is why our proposal involves putting nuclear generators in bodies of water. That way, more communities can be reached, and reached from a safe and agreeable distance.
Nuclear reactors initiate, contain, and control nuclear chain reactions. Reactors can be used in many ways. They can generate electricity, move aircraft carriers and submarines, and produce medical isotopes for imaging and cancer treatment. The core of a nuclear reactor contains uranium-235, which is a very rare fissionable isotope, along with control systems and structured materials. 1 kilogram of natural uranium can generate as much as 10 tons of oil. In present day, there are over 400 reactors in the world, with 100 units in the United States. These 100 units produce 19% of the country's electricity. There are many present designs for nuclear reactors. There are many different kinds of nuclear fuel forms and cooling materials that can be used with varying processes. The pressurized water reactor uses cooling water that is kept at an extremely high pressure so that it does not boil. It goes through a heat exchanger and transfers heat to a second coolant loop, which is used to spin a turbine. They use oxide fuel pellets stacked in zirconium tubes, or burn thorium or plutonium for fuel. The boiling water reactor is the second most common reactor. It is similar to the pressurized water reactor, but only has one coolant loop. Canada deuterium uranium reactors contain heavy water. The hydrogen in heavy water has an extra neutron, so instead of hydrogen, it is called deuterium. These reactors only operate using natural uranium-235. Sodium-cooled fast reactors are cooled by liquid sodium metal. Sodium is heavier than hydrogen, allowing neutrons to move around at higher speeds. They can use metal or oxide fuel and burn a wide variety of fuels. High-temperature gas-cooled reactors use very small fuel pellets. Gases such as helium or carbon dioxide are passed through the reactor quickly to cool it. Because their power density is so low, these reactors are seen as promising for the future of nuclear energy. Molten salt reactors use very hot fluoride or chloride salt as a liquid fuel instead of the solid fuel used in most reactors. There are many different types of molten salt reactors, but the liquid fluoride thorium reactor can generate the most energy. This MSR has thorium and uranium dissolved in a fluoride salt and can get enough energy out of our natural resources of thorium minerals to provide for the whole planet. The USA accounts for more than 30% of the worldwide nuclear generation of electricity. From 1980 to 2013, the generation of electricity nearly doubled from 11% to 20%. The limitations for nuclear plants are how much coolant is available and how many people the energy produced by the generators can reach. The limitations for nuclear power plants right now is not the amount of fuel available, because U-235 production is steady and abundant in the market. These plants generate excess electricity for the communities they power. The limitation of nuclear power is location. Radioactive waste is a major limitation in nuclear energy because it is very hard to get rid of. The waste produced by nuclear reactors needs to be disposed of safely due to its extreme toxicity. Nuclear power plants require external dependence. Not many countries have uranium mines, and not all the countries have nuclear technology, so they have to hire both things overseas. Reliance on outside entities, such as suppliers, can be costly. Nuclear reactors are limited by the lengths they can reach. It is hard for them to reach areas without large bodies of water. That's it.
It all started in 1789 when uranium was discovered by Martin Klaproth, and he named it after the planet Uranus. 100 years later, in 1895, Wilhelm Röntgen discovered ionizing radiation by passing an electric current through an evacuated glass tube and producing continuous X-rays. Advancements in atomic theory steadily continued, and the discovery of the neutron in 1932 by James Chadwick was vital to the innovation that would lead to nuclear reactors. Later, in 1932, Cockcroft and Walton produced nuclear transformations by bombarding atoms with accelerated protons. The next year, Enrico Fermi found that a much greater variety of artificial radionuclides could be formed when neutrons were used instead of protons. Fission is the splitting of the atom, which results in the release of energy. It is named after binary fission in biology. Before pursuing fission energy as a means of producing large amounts of electricity for the benefit of the public, it was undertaken as a means of creating weapons of mass destruction. The first scientists to officially acknowledge the process known as nuclear fission were two German physicists, Otto Hahn and Fritz Strassmann. In 1938, when they successfully split uranium atoms into two or more parts, they then expanded on this idea when they recognized fission as a potential way to form a chain reaction, which would be able to produce more energy and continuous energy without the need for constant triggers. The two German physicists also discovered that the energy released in a fission was about 100 million times greater than the energy released in a chemical reaction. In order to advance the research on uranium, nuclear fissions, and the potential to produce energy, thanks to new knowledge due to Einstein's revolutionary theory of relativity, three American scientists, Szilard, Wegener, and Teller, would need considerable amounts of funding, and so they approached the government. They wrote a letter to President Roosevelt, warning of nuclear weapons, and had Einstein sign it and send it. Roosevelt authorized a small study into uranium. In 1942, Fermi successfully created the first man-made nuclear chain reaction in a squash court under the stadium at the University of Chicago. From that point, because of World War II, scientists worked on nuclear fission as a means of creating atomic bombs, the technology of which would turn to be used to develop modern-day nuclear power plants. Before the production of atomic bombs, scientists already knew that to cause nuclear fissions, uranium-235 had to be extracted from uranium ores, which were used as nothing more than a colorant for glass and ceramics. After successfully creating the first man-made nuclear reaction, Fermi became one of the leading scientists in the Manhattan Project. The American government quickly built many underground cities in order to test nuclear fissions and the physics and chemistry that would be involved in splitting atoms. Working quickly, the first atomic bomb was tested in July 1945 in New Mexico. A month later, on August 6, 1945, the first atomic bomb was dropped on Hiroshima, Japan, and the second was dropped 3 days later on Nagasaki, ending World War II. Only after the end of World War II did nuclear power become available for use in civilian power plants, thanks to the Atomic Energy Act signed by President Truman in August of 1946. Later, in 1953, President Eisenhower started the Atoms for Peace program to not just allow, but promote commercial uses of nuclear power. The nuclear reactors that civilian power plants would use were based off of nuclear reactors used to power submarines. In 1954, the first nuclear-powered submarine was launched by the U.S. Navy. Developing a nuclear-powered submarine was important because it forced physicists to develop safe, stable, and small nuclear reactors that would lead to a world of possibilities in the applications category. After constructing working nuclear power reactors, research went towards improving on previous designs in every possible ways, with extra attention going to both enriching the uranium and changing the type of coolant used. Researchers experimented with all types of uranium, plutonium, using gases, waters, and liquid metals. After the construction of nuclear power plants for civilian use up into the 1980s, innovation of nuclear power and fission stagnated, both because the labor shortages and delays brought the price of nuclear reactors up, and because of the Chernobyl and 3 Mile accidents slowed developments and decreased public approval of nuclear power plants. Since the 70s and 80s, many laws have been passed to ensure the safety of nuclear power. While they attempt to protect the lives of those who live next to nuclear power plants, nuclear power is already safe, much safer than plants powered by fossil fuels, and the many laws only work to increase the costs to both the producer and the consumers of nuclear power. Furthermore, the first and second generation plants are soon to become decommissioned, but the technology in the fourth and fifth generation plants that are being built and will continue to be built for much safer and efficient. In America, several states are in the process of building fourth generation nuclear power plants that will provide a surplus of power to large cities and their surrounding areas. In China and Korea, nuclear power will soon become the staple, with both countries soon rolling out large fleets of fifth generation power plants that will be constructed in record time thanks to modular building. Taking cues from submarines and hovering power plants, the team envisions that in 20 years there will be nuclear power plants on platforms with the ability to be relocated across coasts and oceans to provide power to communities in need. Said power plants will be short-term solutions to all kinds of emergencies, providing days, weeks, or even months of energy to communities in order to expedite recovery from extended blackout, guarantee enough energy during periods of heavy use, and facilitate rebuilding. They could also be permanent power plants used as long-term energy solutions. Historically, large cities have always been near bodies of water, meaning that power generated by nuclear reactors has the potential to reach the most people when the reactor is located in a body of water. Submarines have been using nuclear reactors to generate their electricity since long before nuclear power plants have been built for public use, proving that nuclear technology is safe for use in seas. Also, coal power plants have been built on board ships for centuries, providing all the power for the potentially huge boats. Furthermore, there are hovering air turbines being manufactured that can be moved over land and can provide enough energy for small communities to use. As a group, we thought we could incorporate those technologies into nuclear power plants, with our vision being power plants that float on top of the water and can be moved around to provide power where it is needed. We envision the power plants to be relatively large, not unlike the oil drilling platforms, and contain more than one nuclear generator. Like the drilling platforms, the team's vision of the floating nuclear power plant will have pipes. However, the pipes will not be used to pump oil, but to transmit the electrical energy along long distances, like power lines, from 2 to maybe even 5 miles. There will be multiple pipes because the distance the power plant may need to be from the closest transformers or power substations might be longer or shorter depending on many factors, namely the depth of the water. If there are not any transformers or power substations close enough to the power plant, the best thing to do is build new ones, for it is much cheaper, faster, and safer to build transformers than it is to build a whole new power plant. Another reason why it was envisioned that the power plant would be in water is that nuclear power plants need enormous amounts of water to operate, and there is no better place to get water than the ocean. The most common type of nuclear reactor, the pressurized water reactor, uses tap water as its coolant, but with few modifications, the reactors can also use salt water. Other than a platform to float on, the only extra thing that a nuclear power plant will need on water is a steering system and a captain to pilot it. Other than that, not many things will differ between regular power plants and seaborne power plants. The team believes that in 20 years, the nuclear generators aboard the platform will be 6th-generation nuclear reactors, improving upon the current designs merely on efficiency and safety. Those reactors would need to be modified for life at sea, but since they will be covered by layers of concrete, the ocean water and the weather off the coast will not have much of an effect on them. Special attention will need to be given to the platform, as flipping a nuclear reactor upside down is not safe, to say the least. The problem is not that the actual nuclear reactor would work upside down. It would work very well, and it would be very hot. The problem would be getting enough coolant to the reactor and releasing water vapor into the air by the way of cooling towers. By developing an extremely stable base, those problems could be avoided. Before developing the technology, it would also be decided where the power plant would get its power from. On land, the power plant gets its power from the main energy grid, but that is not available at sea. What these plants could use is hydropower, or, if something goes wrong, have batteries, and finally oil as a backup. Solar power could not be used to power the power plant because there would not be enough surface area on the boat for solar panels to provide power to nuclear reactors. Using wind turbines, another renewable energy, is also not practical because of the potentially damaging waves at sea and the large structures necessary in a nuclear power plant. The final thing that a nuclear reactor needs is a way to get rid of the nuclear waste produced. Worldwide, there are safe methods for the disposal of nuclear waste, with the international consensus being geological disposal. It is safe to transport nuclear waste, and nuclear fuel can even be seen as a resource. Even though it is safe to transport, it must be noted that it is still highly radioactive, and mere seconds of exposure could be enough for acute radiation sickness and maybe even death. That being said, nuclear waste can be transported by special trucks, boats, and potentially helicopters, and will be possible to export it off the plant. One other option when dealing with nuclear waste would be to simply store it underwater, under the platform. Most nuclear waste is stored underwater before being stored on land, and if the platform had chambers to store the radioactive waste built in, that is an option that could be done easily. Plus, the waste could be removed years later when it would be much less radioactive. Our vision is of nuclear power plants that flow up and down the coast providing power when it is needed. On platforms powered by renewable energy, the power plants would be even better for the environment at sea. 20 years from now, nuclear power will be much more efficient than it already is, and with the nuclear reactors powering coming instantaneously from the sea, there will be more space to build on land. On top of freeing up real estate, it would also allow communities to use more of their water and other forms of electricity. For the nuclear power plants at sea would use salt water and generate their own power. With many being against building more power plants on land, the sensible solution is to build clean energy plants at sea, and that is where we think the technology will be headed in 20 years.
Nuclear power plants at sea do not exist today because of many factors. It is opportune to get enough electricity to power a city from a single power cord from a generator miles away. Technology to make long power lines exists, and technology to put them underwater exists, but the cords are not flexible. The technology to plug in an alternate power source exists, but the technology that puts all of these together does not exist. In 20 years, there will have been enough research so that these are a possibility. There are 439 nuclear reactors worldwide, meaning that every year up to 439 years of research can be done on nuclear technology. In 20 years, that is over 8,000 research years of information on nuclear reactors, guaranteed to come with breakthroughs necessary to make the team's vision of nuclear reactors become a reality. For safety at sea, scientists will need to look at where the barge will be located and make each barge specific for a certain area of the world. Each coast is different, so each platform would be unique. Coasts vary in depth. Some are shallow, some are deep, some are rocky, and some are turbulent. When developing the mile-long power cords, the right materials need to be utilized in order for the lines to last for years, maybe even decades at sea. The power lines need to be flexible enough to be rolled back into the platform, while still being powerful enough to carry ultra-high voltages. It would also be necessary to have transformers able to distribute all that energy without fail. Power plants have very delicate and precise instruments measuring the energy output of the generators. At most, 2% of the electricity from the power lines are lost in transition from the power plant to the transformers. By measuring the electricity that passes through the transformers, it can be proven if the power lines and the nuclear reactors aboard the nuclear power plant platform are working.
Nuclear technology has come a long way since when nuclear fission was first proved to exist in an experiment by Otto Frisch in 1939. And it can still be changed and improved upon in many different ways. When choosing in which direction the technology could and should be headed, many different concepts were explored and discussed. Specifically, hovering power plants, using weapons-grade U-235, and using both liquid sodium and water in a single plant. Nuclear power is the only alternative to fossil fuels that is able to consistently and safely provide enough power to power the ever-growing world. Just for the US, nuclear power accounts for over 20% of the total energy used. And all that energy is generated by only 100 nuclear power plants. One way to improve upon nuclear power is to improve upon how many people it can be reached. After all, the point of nuclear power is to provide a fast, environmentally friendly, safe, and efficient alternative energy source to communities that need it. If there were not 7 billion people in the world, then there would be no need for the energy generating capability of nuclear reactors. Nuclear reactors are important because they can generate thousands of megawatts per hour, something that modern day cities and communities need and other technologies cannot consistently provide without dangerous amounts of pollution. One way to improve upon nuclear power is to make it more readily available to more places around the world. An alternative researched was hovering nuclear power plants, not unlike the hovering wind turbines that are currently being manufactured. This option was decided against because it would be too hazardous to move a nuclear generator, and being able to provide enough energy for the coolant for the power plant anywhere it went would be too costly. On top of that, too much energy would be wasted keeping the power plant hovering, for a nuclear generator is much heavier than a wind turbine. No energy is wasted keeping an aquatic power plant afloat. The next alternative option was using weapons-grade uranium. By using weapons-grade uranium, much more energy would be produced in the fissure, and much more energy would be produced in a nuclear generator. But more energy comes at a cost. It is both very expensive to produce weapons-grade uranium, and it has to be refined countless times, being much more radioactive than the 3.5% uranium-235 used in power plants today. This technology was not chosen because of the weapons-grade uranium means more weapons, and the energy produced using this fuel will be more expensive to the consumer than energy produced at sea. The third alternative option discussed was using two coolants, water and liquid sodium. Liquid sodium is heavy, meaning that the neutrons travel at faster speeds with liquid sodium, allowing for faster burning of fuel. The liquid sodium would then heat up the water pipes and cause boiling water and steam, which is more effective at spinning turbines than liquid sodium. This route was not chosen because of the cons of both coolants would be present in the reactor, making the reactors more costly in terms of safety. It was chosen instead to head with floating power plants, because they would reach more people while putting less people at risk.
The team goal for nuclear energy in the future technology is a nuclear power plant that floats and moves along the coast, where there is very little danger of harming humans. If anything were to go wrong with the power plant, and it were to explode, it would be very unlikely that the radioactive waste released into the air and ocean would harm or even reach society. Plutonium is mostly a byproduct of nuclear reactions, where some of the neutrons released by the fission process convert uranium-238 nuclei into plutonium. This element is fissionable, and its most stable isotope, plutonium-244, has a half-life of over 80 million years. Although this element may be the future of nuclear energy, if introduced into nature, it could be very harmful. Another consequence is the chance of a nuclear accident. Although there have been many steps taken to prevent such a thing to happen, there is still a chance that a disaster like Chernobyl or Fukushima might happen again. The smallest radiation leaks could have devastating effects. When nuclear waste is being transported from a floating power plant, the vehicle could crash in the water and have a lasting effect on sea life. A positive consequence is that nuclear energy is clean air, carbon-free electricity, and produces no greenhouse gases or air pollutants. Nuclear energy has one of the lowest impacts on the environment of any energy source because it does not emit air pollution, isolates its waste from the environment, and requires a relatively small amount of land. Positive effects of the future technology could be cleaner air, which would in turn preserve the Earth's climate. Of all energy sources, it produces the most electricity relative to its environmental impact. As a result of the future technology, providing the Earth with cleaner air, preservation of the Earth's climate would mean a disappearance of ideas such as global warming or creations of holes in the ozone layer. Power plants that are bad for nature could shut down, taking away the risk of workers or anyone to breathe in the polluted air.
The 3 reactors seen here are talked about in the present technology section. Each of them have their pros and cons, but in our future technology, we decided to use the pressurized water reactor, but instead of using tap water, using salt water. The cooling towers are put here to show that they produce no pollution. Instead, all that smoke that you see coming out is not actually smoke, but only water vapor. These 3 nuclear reactors all work the same way, only use different types of coolant. In the boiling water reactor, the coolant is much hotter than in a regular pressurized water reactor. The molten salt reactor uses molten salt. It is a liquid metal. The neutrons travel faster in the molten salt reactor. The faster neutrons means a hotter coolant, and the hotter coolant means that the turbine can spin faster and produce more electricity. This is the most common type of water reactor, the pressurized water reactor.